This chapter, we're going to take a look at multiple forms of regression. So, regression is a really powerful tool because it lets us examine some things that are different from hypothesis tests and slightly related to correlation. So, it lets us know how exactly are these two things related. So, correlation tells us, oh, they're related, but regression gives us information on exactly what that relationship looks like with the strength and direction. It's a pretty good predictor of the power of an independent variable, so how impactful it is. How much of variance of the dependent variable is explained by this predicting variable. So it's a little bit like we're getting into some basic cause and effect, but not directly. And we talk about the unique contribution that one independent variable may have on a controlling variable or covariate. So a simple regression is what we see a lot in the statistics field. A simple regression analysis is just one independent predictor variable. So it's one variable that we're saying, hey, this predicts the outcome, and then a single dependent. That's a lot of what we see because a lot of when we're trying to get these relationships, it's more basic problems. Multiple regressions is when we have two or more predictor variables, but still only one single dependent variable. So if you're trying to choose between which one you would do, if you've got more than one predictor, that's going to be multiple. And whether you're doing simple or multiple, there can only be a single dependent variable. So when I look at the variables that are used in regression, I'm still using independent and dependent variables, but they have to be on an interval or ratio scale. So no nominal, no ordinal ones. They're dichotomous. In other words, categorical variables with two categories can also be used if there's a special form of regression analysis called logit regression. So that's kind of where we're forcing a categorical variable to fit in terms of this, but the majority of the time we don't see that. There are some benefits to regression over using correlation. It gives us more information. It lets us think about the relationship in a more intuitive way. It gives us a better outcome and a measurement to quantify the relationship. And it also gives us a formula where we can predict if I have this much of my independent variable, then I can predict this is what will happen in my dependent variable. Simple linear regression is going to assume that two variables are linearly related. So that's a really key assumption that has to happen is we have to say that as one increases, the other increases, or as one decreases, the other one increases. It has to be linear. If it's not linear, then we have a problem. The purpose of it is to look at how strong an association is to be able to predict what's going to happen with that linear regression equation, and how the interaction is going to look between the independent and the dependent variable. So again, Excel is going to be doing a lot of the crunching for us this week, but if you notice, this might look slightly familiar to you. This is actually slope-intercept form of an equation, y equals mx plus b. But this time our slope is being the regression coefficient, so that's going to be our slope. And then our intercept, A, is where the regression line intersects the y-axis. So new formula, but old idea. Here's a sample of a linear regression. So is there a relationship between these things? Well, I have to do some calculations. The first thing I need to do is make a scatter plot. This scatter plot looks pretty linear, so my assumption is met. And then with the table, we're going to calculate the regression variable. Again, Excel is doing that number crunching for us. And then once I have that regression variable, I can see where it intersects the y-axis. In this case, it doesn't cross the y-axis at all. So it's going to be y equals my regression coefficient times x plus 0. And a lot of times you might notice that it doesn't cross the y-axis and you have a 0 value. Ordinary least squared values is somewhat related to what we look at with standard deviation. We're going to take our observed value, subtract our predicted value, and then square it. This is the easiest and most commonly used regression formula to be able to get a regression variable. It's based on sum of the squares, which is why it looks familiar from standard deviation. So if I want to calculate the regression coefficient, I have my regression coefficient is b, which I know is kind of crazy because it seems like it would be r. R is the correlation between those x and y variables, which is found from the previous method, the OLS. And then I have the standard deviation of my y variable and the standard deviation of my x variable. So Excel is crunching a lot of numbers for us here as we do this. The formula for calculating an intercept, if I want to know where the intercept is and I can't visibly see it, is going to be this formula here. But again, Excel is going to do a lot of this crunching for us as we can view scatter plots in Excel. The regression equation does not calculate the actual value of y, so it's a prediction. Predictions always have a margin of error, so we always say there's some error when I'm using a regression line to predict the independent variable. So in order to calculate the error, I would use one of the two formulas on the side. If I have two regression equations, the one on the left is going to be for a predicted value of y, and the one on the y is going to basically be taking error into account and saying I have bx plus a, but there's some unknown error that I'm adding in. And in a perfect world, that error is going to be 0, but more often than not, that's not the case. So if I want to wrap some words around the idea, is there a relationship? That is going to cue you up for a regression situation. Also correlation, but remember think of this as almost correlation part 2. For every unit that's increasing in x, there's a corresponding increase in y. That's getting back into the linear assumption. Or every additional year of education predicts that we have this much amount of money that's going to be impacted. So when we're finding the predicted values of y at a given value of x, we're going to be basically plugging in the x value to get out the y prediction value. This isn't rocket science here. This is literally, we're going to use Excel to calculate it, and then we're going to plug in that x variable to predict what would happen. So if I draw the regression line, that really tells us if we have a linear regression. So that's why it's so important to get that scatter plot drawn. And then I can actually check this line and say, well, is getting a y value of 1.82 at 9 going to be reasonable? So this is 1.82 is somewhere between 1 and 2. And you can see it's just a little bit off that line. So it's pretty reasonable and the error is pretty small. Again, we just want to really emphasize the regression line is not perfect. It is a prediction. And predictions mean that we have room for mistake. Now, a multiple regression is going to provide us more information than a simple linear regression. It's very powerful in the sense that I can start looking at multiple factors that might result in an outcome. But again, it's going to have one dependent variable. So an example of this could be the relationship between education, income, and length of time out of school. So we may see that both of these factor into income. An example of a multiple regression could be the scenario that's given below. I could see that two predictor variables, when combined, may have more significance based on the outcome. I can test whether a predictor variable is significantly related. I could see which of the two is a stronger predictor, or I could test if it's actually related, which is sort of like a backward ANCOVA. So those are all possibilities with multiple regressions. So let's say I have this table and here's my data. I've got two x values and I've got one y value. So my y is my income, my x values are my predictors. So if I look at the table, what does it tell us? Well, the data presented in the table is partially helpful because I need to actually look at that scatter plot to make sure they're linearly related. And I need to answer some questions about that table. How much variance in income do they explain together? And then how much variance is explained by them independently? So if I just look at one factor in the outcome. So to answer those questions, we're going to run that multiple regression analysis. So we're going to begin by getting that Pearson R coefficient for all three variables that Excel is going to help us with. And that's going to reveal that education and years has the strongest correlation. Look at that, 0.826 as compared to 0.695. Once I see that Pearson correlation, then I know we've got some predictor variables with a pretty strong relationship. In our current example, both are pretty strongly coordinated because I basically got 0.7 out of the other one. In addition, those predictor values explain a unique or independent part of the dependent variable. So if I'm looking at standard variance, I'm looking at how things add up, and stronger correlations among those predictor variables, we're going to call that multicollinearity. So when I see that there's multiple things that are strongly correlated, that's a vocabulary word we use because it can cause problems in a multiple regression analysis because it's difficult sometimes to see the unique relationship between each individual predictor variable. So if I was looking at sample multiple regression results, this would kind of be one of the outputs that I would see. So there's a lot of things going on in this image that we're taking a look at. So first of all, we get an R value of 0.946. That's my multiple correlation coefficient. It gives us a measure of correlation between two predictors when they're combined. So combined together, these are pretty powerful. When we get an R square value of this, that's the coefficient of determination for my predictor variables. And it gives us a percentage of the variance that's going to be explained. So about 90% of the variance is explained by these predictors. And adjusted R square is accounting for the fact that there's probably going to be some error in those calculations. So if I look at an ANOVA result, I know that an F value of 30.5 with a corresponding p-value of 0 gives us a statistically significant result. The same is true with this situation. If I'm looking at regression coefficients, between last week and this week, it's really easy to get tied up in those regression coefficients. So an unstandardized regression coefficient is found in column B. So thinking back to that table I showed you, column B is where we're going to find that information. In the column labeled beta, I'm going to get standardized regression coefficients that are going to be presented. And the columns with t-value and p-value, I'm going to get measures that allow us to determine whether or not the prediction variable is statistically significant when looking at the dependent or the outcome variable. In this example, both of these are significant predictors of income. Again, it's like we're doing cause and effects, but we can't definitely say, yes, this causes this other thing. We can say it predicts. So it's almost like you have to be careful of having a really assertive answer here because there's still some room for mistake. And then we have our summary slide. So this concludes our journey through statistics by looking at multiple regressions. This is probably a video you might want to watch more than one time just for a little bit of extra insight. And I hope you've enjoyed the journey.